Hi students, today we are going to see the chapter Force and Laws of Motion in detail. The video program and the same. So after this particular session, you must be in a position to understand the force, its definition, different types of forces, of course its units, how to measure the force, and then as far as laws of motion are concerned, different laws of motion like Newton's all four laws of motion. So what are exactly laws of motion? So how they govern these laws, how they govern the motion and all. So in mathematical form as well, the laws, Newton's first law, second law, and third law. Then we have finally, we end up with, yes, we end up with some applications. Now, so let me share the screen. Now, as you are seeing, so first one, yeah, as I just told you, the major points covered in this section are first law of motion, and consequently we study inertia, mass, mass for inertia, like with different masses, how the inertia would be, its units, then friction force, and how it is it is applied. Now then the second law, definition of force and units. Then after second law, we'll also study the momentum, law of conservation of momentum, and finally we'll define third law with its applications. Next. Now coming to first law of motion proposed by Newton. This particular this particular law governs majority of the actions in nature we observe from day to day. Almost daily we observe these laws in some way or other part of life. Now, if you look at the definition first, so this is, we can see an object continues to be in a state of rest or uniform motion along a straight line unless and until acted upon by an unbalanced force. So this is the law. This is the first law, the definition of the first law. It says, let us repeat again, an object continues to be in a state of rest or of uniform motion along a straight line unless until acted upon by an unbalanced force. That means what? Whenever an object is there, it can be in two states. One is it can be in the state of rest or it can be in the state of uniform motion. When I say uniform, I mean equal displacements or equal distances in equal intervals of time. So the motion is uniform, right? So the movement is uniform in equal intervals of time. Now here actually there are only two states for the object. One is it can be either in rest or it can be in motion. So an object continues to be in a state of rest or uniform motion unless acted upon by an external force. So here we need an unbalanced force to change the state from either from rest to motion or from motion to rest. That means you can see here a body in a state of rest continues to be in the same state, and that of uniform motion also continues to be in the same state unless and until compelled by an external unbalanced force. So here there is a very specific pointing that the force must be unbalanced. So we have to define here balanced and unbalanced forces. So as the name implies, balanced forces mean, so when the forces act in the opposite directions in such a way that compensate each other's magnitude, they are said to be balanced forces. On the other hand, if one particular force dominates the others and it can cause some motion in a particular direction, it is said to be an unbalanced force. Next thing, we can see a picture depicting first law. Like you can see every body continues to be in the same state of rest or of uniform motion. Now here you can see a pendulum bob, so which are actually hanged to a particular rigid end. So here we can see if there is a small deviation given from its so-called position of the state of rest. It keeps on moving. It changes and its state will be keeping keeping on moving, and it will hit. So like that, if you can do such an experiment, wherein if you take such a equipment and just give some displacement from its mean position, it will continue hitting the other one. Like that, if a body is just changed from its mean position or rest, so it will be continuously moving. It will be continuously moving. Now, so this is from state of rest. Similarly, we can also observe for a state of uniform motion also. Now, this particular experiment will prove us Newton's first law, where we have to see that a body which is in the rest continues to be in the same state. Whereas here actually those balls are those pendulum bobs which are in the state of rest. They continue to be in the same state. And the one which is displaced, so we'll hit the others, and we can see that these the ones which are in the state of rest, they continue to be in the rest only. Next, now we define an important parameter called inertia. So, and mass for inertia and its units. When we say inertia, it is the natural tendency of an object to resist staying in their state of rest or uniform motion. So very quite often we use this term in the place in lieu of the word laziness or something like that. So here inertia means it's a natural tendency of an object to resist the change in their state, whether it is from state of rest or of uniform motion. So the natural tendency that it will not change its position unless and until an external force acts upon it. Now, it can be compared to laziness in human lives, and mass of an object is a measure of inertia. So chiefly, what is a measure of inertia? End of the day, it is the mass. The amount of matter present in the body is a measure of inertia. So therefore, we can say uh, chief cause for inertia is mass only, and its SI unit being kilogram. Right. Now, next thing. So as I just told you, it is inertia we have seen. So inertia can be defined in two ways: inertia of rest and inertia of motion. So the body which is in the state of rest will continue to be in the same state of rest, and so on, just like that. We can also define for a state of motion. Now, so inertia of rest can be proved experimentally by taking a setup like this. So this is the experiment you can see on the screen. That is the experiment to demonstrate inertia, wherein we have taken a coin. You can also just do this at your homes as a project. So here, if you take a coin, 1 rupee coin like that, so this particular coin is placed. Now you can see is placed on a glass tumbler or a glass of water. So actually, it is placed on a piece of cardboard, and then here we can easily observe the state of inertia, that is inertia of rest. If you all of a sudden, if you just change, if you move, because on the glass water you have, on the glass of our tumbler you have here a piece of cardboard on which coin is placed. So when the cardboard is just fastly moved in one direction, so automatically the coin that is placed on it automatically falls into the glass because of inertia of rest. So whereas the part of the cardboard or the piece of cardboard will be moved in one direction. So as is shown in this diagram, so with some external force. So because the coin will not come to the state of motion immediately, because so far it is in the state of rest and it wants to be in the same state of rest. As a result, the coin falls down exactly in the water. So this is the best example we can see and show for inertia of rest. Now here we have to define friction force. What exactly friction is? So under what category it comes? As we are mentioning here, in the name itself implies it's a force. Friction itself is a force. Now friction or force of friction always opposes motion of objects. So we quite often we see, and we might have studied some of the applications, and friction force is one of the most important forces that we need for our day-to-day life. So even for just walking on the road or a floor, or just for writing just with a mere pen on the paper also we need some friction. Now here force of friction always opposes the most of the objects. So friction comes into force or effect when only one object slides on the other or tries to roll, or whenever an object is moving. So when an object is trying to move on another this one surface, so here the force of friction always opposes the most of the objects. Particularly, it is relatively caused by the surface in contact with the object in motion. So basically caused by the surface in contact, because so there are so many irregularities that we cannot see with naked eye unless and until they are taken with microscope. We can see these irregularities. So the irregularities between the surfaces, they bind each other, and as a result we have the frictional force is caused. So accordingly there are various friction force, like we have static friction, we have dynamic friction, we have rolling friction and sliding friction as per the case may be. So as the names are implying, so when an object is trying to roll on another object, so the friction is said to be rolling friction. Similarly, when it is trying to slide on another surface, it is said to be sliding friction. And we have other like static friction and dynamic friction. So these are the varieties of frictional force. Okay. Now when the body is in the state of rest, exclusive rest, we can say it is static. So like that we can define. And next, you can see here actually a particular figure. So wherein you can easily observe friction force, how it is caused. Now here you can object a man is pushing a box like this in this direction. So here, if you look at, so if you take the free body diagram of the same, here I must mention one point, that a free body diagram of an object is a diagram which will reflect different forces acting on it. So as the name implies, a free body diagram is a diagram wherein we can have all the forces, directional forces, different forces acting in different directions, so that finally we end up with calculating the resulting force, right? So that's what it is. So see, force actually, you can see here, there are two things here. One is free body diagram. If you look at, so force, it's actually application of the force in this direction as shown above. So the friction force always opposes the motion. So this, as a result, we have a static friction in this direction. Now, so static friction, there is no motion, and sliding friction, there is motion. That's what. So here, as long as the object is not moving, but still we have a frictional force called static friction. So that's the reason why it is merely a static friction till some time. Then when the object just starts sliding on another surface, then we have sliding friction, and so there is a change altogether. So that's how it will be there. You can see a graph over here when actually frictional force is taken against applied force. So as the applied force increases, friction force also increases to some extent linearly. So you can see in the graph that it is going linearly, where it is a straight line. So till here, till this point, it is a straight line, and it increases linearly. So that means what? So when we draw a plot for friction force against the applied force. So friction force is the effect of applied force, because the man is exerting some here. So here, because he is exerting, that means what? He is applying some force in one direction. So that force is to be taken on the x-axis, and frictional force is to be taken on the y-axis. If you take these two parameters like this, and as long as the object doesn't move, that means applied force is applied till this extent. So why the object doesn't move? Why it is not moved? Because the weight itself is very high, and when compared to the weight itself is very high when compared to the application of the force applied. So therefore, because of its own weight, it offers resistance. It offers opposition for the movement. So initially it doesn't move at all, though he is applying force. So that's what we can see in the plot in the initial stage of the graph, where it is linear. So that means it doesn't see, it increases linearly. Frictional force, as we apply force, as we continuously increase the apply force, then friction force also gets increased in order for the object not to move under any circumstances. Now there exists a point where it gradually slides. So if you keep on increasing the force, applied force, there exists a stage where it gradually starts sliding on the surface. So there actually it's no longer it's a static friction, it is a sliding friction as it is mentioned here. So from here gradually So because the now, see, you can see a drastic, a very much random slowing, narrowing of the this one. You can see graph actually. So all of a sudden randomly it got reduced. So friction force gets reduced and it starts sliding. So that's how sliding is also uniform. As long as friction applied force is uniform, sliding, that is frictional force, is no longer, you don't have, no longer you have frictional force, and frictional force is constant. So because the frictional force is constant, the body starts moving. Frictional force is constant irrespective of applied force. That's what you can see from the straight line path, but is not linearly increasing from the straight line path, which is parallel to x-axis. You can see it just slides. It just slides. That's what we can see. Now, in the next slide, we can see second law. So, coming to the rate of change of momentum, second law gives us concept to look at rate of change of momentum. So here there is a parameter called momentum. Just we are we have been seeing now of an object. So the rate of change of momentum of an object is proportional to the applied unbalanced force. So this is the main definition of Newton's second law. So Newton's second law relates force, the main parameter force, and momentum. So rate of change of momentum of an object is proportional to the applied unbalanced force. So always in the case, the rate of change of momentum. That means you can have momentum actually is given mathematically as m into v. So therefore, a final momentum and an initial momentum, if you consider at two different points of time, then the change in momentum with respect to time is said to be, it is said to be force applied. So m into v minus u by t. No, it gives the definition of force as I just told you, because force is mathematically defined as mass into acceleration. Just now I told you m into v minus u by t, that's m into a. So the rate of change of velocity is nothing but acceleration, and as such force is nothing but mass into acceleration. So therefore it gives the definition of force, and the SI unit of force is said to be either it is Newton or kg meter per second. So it is a SI standard system of international units. So Newton is the main unit. So like we have, it means a force of 1 Newton. So if you have to define 1 Newton force, because see here it is also defined as 1 kg meter per second square. So it means force of 1 Newton on a mass of 1 kg causes an acceleration of 1 meter per second square. So if that is the case, then the force applied is said to be 1 Newton. So that means a force of 1 Newton or 1 unit is on a mass of 1 kg causes an acceleration of 1 meter per second square. So that's how we see the Newton's second law. Now you can have here actually, if you apply more force to an object, it accelerates at higher rate. That's what you can see. Typically this we see in different day-to-day activities, like in railway stations we have. So where actually where they'll be, these people, the working people over there, they'll be pushing some kind of masses, right? So you can observe here actually when the force is applied with the, with different magnitudes, you can see the acceleration. So when your force is of this much magnitude, you have a corresponding acceleration of that much, and your force is increased, then you have more acceleration is also increased. That's how it goes. Next thing, that is what Newton's second law. Rate of change of momentum is equal to applied force. Now, so just now, as I told you, momentum, if I have to define mathematically, it is a product of mass and velocity. It's an important parameter of interest you have to study, and is represented by the symbol P. So m into v is actually, and SI unit, as I told you, kg meter per second is also another unit, because kg, whereas kg is the unit of mass and the meter per second is unit of velocity. As a whole, for the product m into v, that is mass and velocity, we can take kg meter per second. So as an unit. Next thing is, so it finally we have no example here. Actually, momentum real-time example, like when two objects are coming, like with different masses, when they are just coming in one direction, right? In the sea, in the opposite directions if they are coming. So you can see over here there are two masses m1 and m2 kgs which are traveling with v1 and v2. That is before collision. So they have not yet collided. Actually, they are coming in individual paths. So that's the reason why you can see it here. It is only before collision. Exactly during collision, because there exists a time interval where they collide with each other. So that is the time interval if you take and you analyze. So therefore, actually masses will remain unchanged. Only thing is, so here during collision, actually, we have very one important thing to be observed, which is the basic of Newton's third law. So because each and every object when collides with another object, so it experiences some force. Understand? So therefore, the force experienced with the first body and the second body is given by F12, and similarly, the force experienced by second body and first body is given as F21. So as I just told you, F1 is 1 is equal to F12 is equal to minus F21. Okay, that's why you can simply take F12 is equal to minus F21. So that's what we see here into delta time. Here actually we are only calculating with respect to, yes, we are calculating with respect to what? With respect to, you can see here it is F12 into delta T is equal to minus F21 into delta T. That's what we have here. So always they are opposite and equal in magnitude. Then next thing is third law of motion. It's very, very important motion, which is the crux of the entire space governing formulas. Third law of motion, and for every action we feel and we see that there is an equal and opposite reaction in terms of magnitude and direction too. So it is implied that they act on two different bodies. So it is implied that they act on only two different bodies. Whenever third law is there, that particularly when whenever equal and opposite reactions are there, so they do not act on one single body, rather they act on two different bodies, right? So we have to see now, right? So it is implied that they act on two different bodies, just I told you. So it is an isolated system basically. So that is as there is no external force, right? The total momentum remains conserved as an effect of third law. As I just told you, momentum before collision is equal to momentum after collision, and as such, the total momentum remains conserved as an effect of third law. So we have some doubt here. So third law of motion is applicable everywhere and anywhere. So there have been innumerable number of examples where we observe this third law, right? So in Hindi, there is a saying goes, "Kuch pana hai to kuch kona hai." That is also, we can say, that can also be derived. So we can see now Newton's third law, a typical example. We apply this Newton's third law particularly in the launching of the rocket pads. So here force on a rocket react, it will be there. So that's what it is shown as reaction. So rocket moves up, force on gas is action. So hot gas comes out of the nozzle. So that is, you can simply say it is the effect of Newton's third. So like, that is the reason why balloon moves. See, a hydrogen filled balloon will go to the top, and the air pressure will be the bottom. So here also in the case of rocket, actually at each and every stage, you can observe that force on gases is in the opposite direction, and force this one. So force on rocket. So what is the reaction and what is the action? Like that, we can see so many things. So finally, rocket moves up, and because it expels gases outside in the other direction, it moves up. So that's what is the best example that we can quote for Newton's third law. So this is the actually end of the lesson, forces and laws of motion. Now we have seen basically in brief what are the different laws of motion, how and where they are applied. So we have a sample sheet over here for the students to complete this in all aspects. Thank you.